So, welcome to this lecture series. It's our first lecture series on statistics. We're going to be giving today a brief introduction to some statistical concepts. Keep in mind here that the point of this lecture series is not to provide a detailed introduction to statistics. Those are more easily available online at places like Khan Academy, with links provided on the Google class page. But instead, the goal of this lecture series is to try to help put some of those concepts that you're going to potentially have been introduced to in the past or might need to sort of review some on online sources, put them into a context of the behavioral research we've been discussing in this class, and also try to link them up to some of the work we're going to be doing in the R statistical language. So first of all, let's just start with a basic understanding of basically the two classes of statistics we're going to be working with. First of all, a statistic is nothing more than a characteristic of some collection or sample of data. So this can be data that you collect in an experiment, data that you collect from text analysis. Anything that can be quantified, in essence, can be described in terms of its characteristics of this quantified data, even things that are simply quantified in a nominal sense can be both described and inferences can be drawn. So just to briefly then introduce the idea of descriptive statistics are a way of just describing this data. And in particular, the two types of descriptions we're going to be looking at are things called central tendency and dispersion, but there's also aspects like skewness, other sort of ways we can describe the basic shape and of the data collection. Inferential statistics are what allow us to make probabilistic inferences from samples to populations. So one of the things that we talk about a lot in this course is the idea that we're often taking some sort of a sample, and we might want to though make claims, i.e. sort of generalizable claims, about some larger population. And so that's where we need inferential statistics. But one thing to keep in mind is that descriptive statistics, which probably many of you worked with without knowing it throughout, from elementary school almost on, are that there's no, you don't have to make any assumptions about whether or not you can in fact draw inferences or not in order to be able to describe something numerically. So these are distinct ways of talking about data. Another important distinction in the world of statistics is thinking about univariate, bivariate, and multivariate. If you're familiar with these prefixes, obviously the idea is that we're talking here about the number of variables that are involved. Again, remember that a variable is some measure of a construct. And a univariate analysis or univariate statistics are when you're trying to describe one observed variable. Bivariate analysis is where you're looking at the relationship between two variables. And multivariate is actually capturing the simultaneous covariation and relationships between three or more variables. We're going to be dealing primarily with univariate and bivariate analysis in the first week or two of this statistics section, and then we will be introduced though to multivariate analysis or multivariate regression later in this multi-week statistical series. So we'll be going over these more detailed class, but I do want to include here just briefly these different R commands that you might be using. So when you go to a data set, even before you've done anything else, you might need to be able to read the data in and also do some quick analysis of it. So these are just some ways that things to help you remember about how you can figure out which variables are in your data, how you can figure out how many cases are in your data, maybe do a quick table, etc. Again, we'll be talking about these in more detail, but I do want to keep these in here so that you can refer back and see some of the commands. So first, let's think about the basic univariate statistics. Now, my guess is that most of you, again, should be very familiar with the concepts I'm about to talk about, but I'm going to try to put these into context, again, of the language we're using in this course, and also, again, how some mathematical background if you aren't familiar with it. So first of all, when we talk about describing a variable, one of the things we might be interested in is just a frequency table. So basically, we have some observed variables, and there are a certain number of answers people can give. So we have a 7-point question on a survey, and we want to know how many people give, the first answer, second answer, third answer, fourth answer. Or we have a survey, and we have an indicator for whether or not you're male or female. We want to know how many males and how many females. This is a simple frequency idea. In the diagnostic assignment that you were given, for example, we have dogs in the park, and somebody writes down coat color, brown, black, yellow, tan, and then the number of dogs in each. So this gives you a pretty clear understanding. Now, if you've only got 3 categories, 5 categories, you can certainly learn something from this. You could imagine, though, if you had something like age in a data set, you have a very long list. So the number of people who are 20, 21, 22, 23, and that might be a little bit much. So a frequency table works probably best whenever you are working with a fairly small number of categories. But again, it's basically just think of the frequency as this is sort of the distribution of data that we actually observe, or the distribution of the measured variable. So what we might now want to do, now that we understand something about what the data themselves underlying look like, which is going to be like the frequencies, we might want to think about a more compact way of describing variables, including variables such as dog coat color, but also age or income, where you have frequency tables don't work very well for giving you a bigger picture. So the 2 really big descriptors that we want to think about here are central tendency and dispersion. Now again, central tendency is something that you'll probably have been introduced to. It's mean, median, mode, right? So a mean is going to be an average, the median is going to be the 50th percentile, and the mode is the most common response. Now, it might be easy to think that as long as you've got quantitative data, all one ever needs to think about is the mean. But just to see how short-sighted this is, let's go back for a second and think about our dog coat color. Can we actually give the mean for dog coat color? Not really. So it's often the case that as you work with different types of data, say a nominal data, that you might need to use the mode. If you've got ordinal data where the underlying, in essence, you know that a 2 means more than a 1 or a 3 means more than a 2, but you aren't sure that the actual interval between these is the same, you probably should be using the median. And finally, the mean is quite meaningful when you've got ratio and interval data. Now, there are some cases, for example, when you've got strange underlying distributions where you might need to give a little bit more information, but that's a more advanced topic. Now, thinking about dispersion for a minute, one of the most common ways one thinks about dispersion is just the range of the underlying data. For example, minimum and maximum. So in this example here, we're looking at the time in the park from the diagnostic assignments, and you can see that the longest time, it ranges from, a very short time, just over 0 minutes, probably very few that are 2 or 3 minutes. But the longest might be up to almost an hour, right? 50 minutes or more. But that doesn't necessarily tell you, again, it's not that great of a descriptor because there's not a lot of times that are over, say, 20 minutes. So instead, you might want to do something like the interquartile range, which would give you the sort of 20. So it's very similar to the median that you're looking at the percentiles, but you're looking at the 25th percentile up to the 75th percentile or some other interquartile range. Finally, the most common, the one that corresponds most closely to the arithmetic mean, would be the standard deviation. And in fact, we use standard deviation quite a lot. It turns out that you can even use it in cases where you have nominal variables, even though, again, the underlying math I would leave to a statistics course, but just we tend to use standard deviation a lot as a measure of dispersion of the data. And we'll be talking a lot more during this lecture series about exactly what that means, standard deviation, but hopefully you at least recognize the terminology of standard deviation. We'll also be talking about standard error or variance. Just as a reminder, just so that you can see this isn't scary math, this is what, if you go and look at a statistics course, the equation would look like for the mean. So you basically have, right, the sum of all of these observations of x divided by n, which is just the number of cases. So nothing at all scary. Again, you probably could do this automatically in your head, if I asked you to calculate the mean, but just as a reminder, this is the mathematical notation. So what might, for example, a variable look like that we were going to think about mean and variance on? The one we're going to talk about today is days in a typical week that you review news on the internet. And the categories that you can give are none, 1 day, 2 days, 3 days, 4 days, 5 days, 6 days, 7 days. Now, what's nice about this, as you might be able to see, is that it's actually probably closer to a ratio variable than many we might get in political science, because 0 actually has meaning. It means they have no newspapers. At the very least, we can look at this and think, okay, we can probably go in and could actually calculate a mean on this variable, and it should be meaningful. We should be able to interpret what the mean is and use that as a measure of central tendency. But first, let's just look briefly here at the histogram, or the underlying, in essence, this is the histogram, or a bar chart in this case is actually what we're doing. So a histogram and bar chart, just for those of you who would like to know the specifics, a bar chart means you've only got, say, these 7 categories and you aren't binning. So age, you might use a histogram where you actually have to collapse all the people between 0 and 10, or the people between 10 and 20, and so on. With a bar chart, you're just simply basically looking at the frequency. So this is giving us the relative frequency of the people who said none, 1 days, 2 days, 3 days, and you can see the colors underneath indicate the categories, what each color of the bar is. Now, what you can see is that this is what's called a bimodal distribution. So there's a lot of people at 0 days and a lot of people at 7 days, and not as many in the middle. So that people tend to either read it a lot or not really at all, and few people tend to say, well, just some of the time. Now, when we then go and look at the mean that is not calculated here, it's going to, you can guess, probably end up right around the middle, probably around 3.5 days, based on just a rough eyeballing of this. One thing to keep in mind, though, and we'll be coming back to this in some of our future discussions, is that you could also do a box plot. So here, I happen to have broken them apart, but it's not necessary. So what I've done here is I've actually charted out the box plot for number of days that you've watched the newspapers, but it's done separately for 2 different groups within the sample. So some for males and some for females. So that's actually a bivariate box plot, right? Because we've got 2 different, in essence, we're looking at the distribution of number of days conditional on being male or female. But for now, let's just not worry about that. Instead, think about what we can actually get out of a box plot. So just as a reminder, the box plot, the heavy bar in the middle is indicating the mean. So we can see that the mean for men is around 5 days per week, and the mean for women is around 3 days per week. In addition, we, in essence, are getting the interquartile range, and we get the minimum and maximum. So the box itself represents the interquartile range. So for men, it's up, all the way up from about 1 day per week up to 7. So that's going to basically give us the middle 50%. It turns out that in addition, we must get the additional 25% at 7 days. And then also you can see that there are some men that name 0 days. And in fact, you can see the range for women is the same. It's between 0 and 7. The big difference, of course, is that for women, there are only about 25% of women who are at the 7-day point, because the end of the interquartile range is around 6 days. Now, this is slightly more advanced, but I want to just introduce it because I might be using some of this terminology, and it can be useful for those of you who want to connect what you might have learned in statistics courses into our discussion here. And that is the idea that we're going to think a little bit about variance and dispersion in ways beyond what we've just talked about with the box plot. And one thing to keep in mind is that there's going to be a difference between our population variance and our sample variance, which is less important. What really you should notice in this is that sometimes you will see something like a sigma or the mu, which is what we have on the left-hand side. In other cases, you might see an S squared or an X with a bar over it, right? Just indicating the mean of X. What's important about this is that when you see the Greek letters, it's usually indicating the population variance. And when you see the sample variant, when you see the S's and the X bars, you're actually looking there at sample variance. What you can see also from this is that in essence, when you're calculating the variance, be it population or sample, what you do is you basically add up all the deviations between the X's you observe and the mean of X. You end up subtracting them, so you have a list, and some of them are going to be negative, some of them are going to be positive. You square them all, and then divide it by n minus 1. So basically then to get the standard deviation, you actually take the square root of the sum of all the squares. There are good reasons, which we could go into more detail about in discussion if necessary, as to why you don't, for example, just take the absolute value. But of course, the reason you have to square it is because you don't want to have, if you added up them all without squaring them, it would in essence be 0, because some of them would be negative, some of them would be positive, but on average you expect them to be 0. What is also important about the difference in these nomenclatures is the idea that, in essence, anytime we have a sample, we're going to end up needing to make inferences about our underlying population. The same with the mean itself and also with the variance. So just keep that in mind. We'll be coming back to inferential statistics, but even in the way we want to think about this mathematically, we have to recognize that there is a difference between the sample that we're measuring and what the true state of the population that we might be interested in out there is. So just a quick sort of check here, in case you can try to, again, interpret this fairly basic mathematical formula, is that a standard deviation, what direction is it going to go as sample size increases? Is it going to increase or is it going to decrease? I'll take a second and let you think. Okay, if you haven't yet figured it out, pause and maybe think some more. For those of you, though, that are ready, that recognize here that what is happening is that the standard deviation is actually getting smaller as the sample size goes up. That is because, of course, the term with the n is on the bottom, which means that is getting to be larger and larger as the sample size goes up, and so we would expect it to be getting smaller. So basically it means that when you have a very small sample, you're not going to be as confident. We're going to come back to this idea. But when you have a larger sample, you're going to be much more confident because the estimate of how much variability is going to be smaller. We'll come back to it. But again, what's important is just to know that even if you are sort of uncomfortable with math, you should be able to see when the n is on the bottom that probably standard deviation is going to go in to be smaller rather than larger. Now, again, we'll be going over this more in class itself, but here are some basic R commands that we might be using when we're conducting the sort of descriptive univariate analysis we've discussed about so far. So sometimes we might be looking at a mean or the summary. There are other summary statistics like minimum, maximum, median, quantile, range. You can also, if you need to find out n, you can use the length command. And again, there are variance, standard deviation, square root of variance. In addition, though we probably won't go into in detail here, there are also ways to deal with weighted data. Again, that's a slightly more advanced concept, but hopefully we'll be talking about it some, because we all know that whenever we need to start dealing with actual data, part of what we might need to do is be confident in our external validity or generalizability, and for that we might need to use some commands with weights. But again, that's more advanced. We'll be talking about it in the class. Finally, I want to conclude this introductory lecture in this first series by discussing quickly some tips for presenting analysis, even when we're talking about very basic analysis of the sort of just basically means, medians, histograms, etc. Norms of presentation would include things like describing the variable and coding of the variable in any type of written work. So make sure you don't just sort of say, I measured dog coat color and then just sort of move on. You might want to say, I measured dog coat color. These were the categories we assigned it to, and maybe even talk about how you developed that coding scheme, very similar to what we might be thinking in a measurement type context. When you are discussing the variable, even if you've got graphs, etc., still in words you're going to need to give some sense of central tendency. Again, this might vary depending on what the underlying level of measurement that is of your variables, and variance. So again, you could use mean, median, mode. You could talk about interquartile range. You could talk about standard deviation. And if you see anything else that's noteworthy about the variable. So for example, in the earlier case of the TV viewing, I might want to notice that that was a bimodal distribution, that there were a lot of people at 0 and a lot of people at 7 and not many in the middle. That way, I don't even have to put the table in order to give my readers an understanding of how the underlying data are distributed. If you're describing the variance, you can actually give the standard deviation in parentheses. And in fact, it turns out you can give many things in parentheses. We're going to be seeing whenever you deal with things like t-tests or probabilities. And also remember, if you're reporting numbers less than 1, use 0.xx, not just 0.xx. And that goes even if you're, right, obviously you're reporting numbers over 1, you're obviously using the same, but basically you're reporting numbers under 1 the same as if you would be reporting them over 1 using just the 2 significant digits after. So a total of 3, and in some cases more than 3, but in general we're sticking to 3 significant digits. Now, in addition to some of these more mechanical things, a lot of what you're going to need to be thinking about is how you interpret the data for the reader. So again, you're going to be clarifying what the variable is measuring, as we discussed in the earlier slide. You need to make sure that the numbers in the text make sense. So for example, you don't want to give a mean of something like gender. You don't want to say the mean of gender is 0.56. That doesn't make sense. Like there's no such thing as 0.56 of a woman or a man. You want to say 56% of the respondents were female, and the remainder were male. That would be a way to make sense of the numbers you're reporting. When in doubt, try to keep your numbers grounded in real world quantities as much as possible. So even as you're going to see when we get into more advanced analysis, trying to keep numbers grounded is incredibly important. So you don't want to just throw out there the ideas of there's some change of 0.45. You might want to talk about, well, 45% or 47% of respondents did X or did Y. Be careful to actually inspect carefully any variable you're going to use before you use it. There can be all sorts of issues hiding in the corners, like, oh, the code for 9 was actually used for don't know, not sure. And maybe you want to recode that to the middle. Maybe you want to recode, delete those cases, but you don't want to treat it like a 9 because that just doesn't, you can't interpret that in the same way. As we discussed before, using the correct statistics for the measurement level. And also trying to give some interpretation of relative standing. Is the value that any type of value you're reporting, is it sort of high, low, unexpected? Again, focusing as much as you can on interpretation. Again, and I mentioned before this, distributions might be unimodal, bimodal. They also might be very skewed. So there might be, as in the case we looked at with times of dogs in the park, where there are very few at the tail ends. We might find the same thing with income, and and most of them are clustered towards the end. We'll be discussing in more advanced future sessions how you actually deal with data like that. But for now, just recognize that you try to look at it as carefully as you can, inspect it carefully, and describe it. It turns out it will be very important to build that foundation as we go on to more advanced work. And it's very important for your readers as you try to interpret and analyze the data that you are describing to them.